So I'm going to go over some homework problems related to triple integrals. The first one is just a simple problem of evaluating a triple integral, not setting up anything. So I want to begin then with integrating the inside here with respect to z, and really there's just a 1 here, so I'm just going to get z evaluated from y to x plus y. So I plug in x plus y for z and then y and take the difference, so I get x plus y minus y, which is x. So that means what's inside here is x, and now I'm integrating that with respect to y, and I'm going from y equals 0 to 3x. So this is the second integral we want to do. Again, this was x, and I'm integrating with respect to y now from 0 to 3x. So x is a constant, so I just get y when I integrate this, like the constant times y, and I'm evaluating y from 0 to 3x. I'm going to get 3x squared, then minus 0. So I just get 3x squared. And so the first two integrals are going to give me a 3x squared, and now I want to integrate with respect to x, where x is going from 0 to 2. So I have 3x squared, we're evaluating from 0 to 2. After we integrate, and then we're going to get x cubed here. You can see the derivative of x cubed is 3x squared. Or you can take the 3, integrate x squared, you get x cubed over 3, the 3's will cancel, and you have x cubed. We want to evaluate this from 0 to 2, so from x equals 0 to x equals 2, we're going to get 8 minus 0, or 8. And so 8 is going to be the answer for the value of this triple integral. So that finishes the first problem. Next, for the second problem, I want to find the volume of this wedge here. And let's look at what this wedge is. On the bottom, we have z equals 0 because we're in the first octant. So the xy plane is going to be the bottom where z equals 0. And then the y squared plus z squared less than or equal to 4 is telling us what's going on for this part here. When y squared plus z squared equals 4, we're on the cylinder. You can see it, y squared plus z squared equals 4 is a circle in the yz plane, and x can be anything, so you just move that forward, you're going to have a cylinder. So this is the top part of this wedge. It's y squared plus z squared equals 4 for the top part. Y equals x is this side here that we can see here. So y equals x is this line in the xy plane, and we're just going straight up to get this plane. X equals 0 is the back. Remember, x equals 0 is the yz plane, so that's just going to be the yz plane in the back. Now I'm drawing in this picture what's going on in the xy plane. So I have x and y going from 0 to 2. Well, where does this 2 come from? This 2 is coming from the fact that we had this circle of radius 2 in the yz plane, the y squared plus z squared equals 4. That's a circle of radius 2 in the yz plane. So y is going to be 2 here, and z is going to be 2 up here. So we have 2 there and 2 here. So y is going from 0 to 2, from the origin here all the way to 2. And then this line is the y equals x that's given to us on the bottom here. We're just going to have y equals x. Okay. So the 2 for x isn't important. That's just where y equals x and y equals 2 intersect. You're going to have x equal to 2. So we have this triangle on the bottom. Okay. The y-axis is here, and then the triangle comes this direction to this line. Let's set up this triple integral. Let's see, we have y going from 0 to 2, 0 to 2. And for each fixed y, we want to look at what's happening to x. X is going from 0 to this line where x equals y. X is 0 to y. So this part I just did, this double integral here, these two integrals, dx dy, is just the same as setting up a double integral. I just looking at what's happening in the xy plane. That's why I drew this picture in the xy plane. and I'm setting up what the limits of integration are for this triangle. So again, y goes from 0 to 2. For each fixed y, drawing a horizontal line, x goes from 0 to this line where x equals y. And last, we want to handle z. So we take a point in this triangle in the bottom of this solid here, and we imagine going the positive z direction, and we want to know the first thing we hit and the last thing we hit. The last thing we hit is going to be the cylinder, but the first thing is going to be that triangle. And that triangle is in the plane z equals 0, the xy plane. So we're hitting the xy plane first, where z equals 0, and then we're going straight up and we're hitting the cylinder, where y squared plus z squared equals 4. So I just solved for z here to see what's happening with z. Z is going to equal the square root of 4 minus y squared on the cylinder. Now notice I took the positive square root because we're in the first octant, so z is positive. So we get z equals the square root of 4 minus y squared for this part of the cylinder. So that's the setup for this problem. That'll be the volume, because we're just integrating one here. We're going to get this triple integral for the volume of this wedge. Now we want to integrate this. So we integrate with respect to z first. And again, since there's a 1 here, we're just going to get z evaluated from 0 to the square root of 4 minus y squared. That's just going to be the square root of 4 minus y squared. So the first integral we get inside is just going to give me the square root of 4 minus y squared. Z evaluated from 0 to here. Next, I want to integrate with respect to x. And notice you can tell now this would have made a difference if I had a dy dx instead of a dx dy, because dy here would mean I'd have to integrate with respect to y next, and this is a little hard to integrate with respect to y. So we need to do a trig substitution. But with dx dy, this is not hard to integrate. This is just a constant. So it did help to put dx dy here instead of dy dx, though initially we could have set it up either way. So when I integrate this, I'm going to have a constant times x, this square root of 4 minus y squared times x. X is being evaluated from 0 to y, and that's just going to be y. So I'm going to get this times y. So when I integrate with respect to x, I'm getting that constant times y. This is x evaluated from 0 to y. Now I can integrate this with respect to y, and you can see it looks a little bit more doable now because this y is going to be part of the derivative of this 4 minus y squared if we do a u substitution. So let me show you the substitution. We're taking u equal to 4 minus y squared. We're going to get du is minus 2y dy. I want to know what to do with y dy here. I'm going to replace that with divide by minus 2 here, a minus 1/2 du. So y dy equals minus 1/2 du, and that's what I'm going to put in for this y dy here. So I'm going to have the square root of u, and then a minus 1/2 du. Minus 1/2 we can take out. We're integrating the square root of u du. We're going to get u to the 3/2, because u to the 1/2 is what we're integrating. Get u to the 3/2 over 3/2. So u to the 3/2 over 3/2 times the minus 1/2. So we have u to the 3/2 over 3/2 times the minus 1/2. You remember u is 4 minus y squared. So we have 4 minus y squared for my u to the 3/2 over 3/2, and the minus 1/2 that came from here. So this is just going to be minus 1/3. And we want to evaluate this from 0 to 2. I plug in 2, and this is 0. 4 minus 4 is going to be 0. So that's just going to give me 0. And then when I plug in 0, remember we're subtracting, so this minus 1/3 we get from this part becomes a plus 1/3. And then I plug in 0 here, I have 4 to the 3/2. 4 to the 1/2 is 2. And then I want to cube that. 2 cubed is 8. So 4 to the 3/2 is 8. And again, this simplified to minus 1/3, but we were subtracting, so this is plus is 1/3. So we have plus 1/3 times 8, or 8/3. So that will be the answer for this problem. That will be the volume of this wedge here. Now I'm going to skip 3, 7, and 10 because those problems I wrote out in detail for you in solutions so you can see those. So let me go to 17. Both 17 and 19 are related to switching the order of integration for a triple integral. And in this problem, we want to switch the dz dx dy to dx dy dz. So we want to know what this looks like when I put dx dy dz here. It's going to change the limits of integration on this side. So we can look a little bit at this, what's going on with this solid in this picture. We have y going from 0 to 1. For each fixed y between 0 and 1, x goes from x equals y to x equals 1. So x equals y will be this plane here. X equals 1 will be this plane. We have z going from the bottom where z equals 0. So that's the xy plane to z equals this plane where z equals y. So this picture then is coming from these limits of integration, and they agree with each other. But let's go ahead now and try to analyze this a little closer. So I'll go ahead again and point out what all the different faces are in this picture. That again was x equals 1. That's coming from x going from y here to 1. So x was 1 here. This one was coming from the x equals y. So y equals x there. And this last one comes from looking at z going from 0 to y, z going from the bottom here to the top. This was z equals y here. So that's all the faces except for the bottom face, which is where z equals 0. So we want to set up the triple integral, and we want it to be dx, dy, dz. So first we need to know what's happening to z in terms of numbers here, or we can look at the yz plane. Let me look at what's happening with z. Z is going from 0, that's the bottom, where z is equal to 0, the xy plane. And the biggest z can be is at this point. So what is this point? Well, x equals 1 on this side, y equals x here. So those two intersect where y equals 1. Y equals x, x equals 1. So x and y both equal 1 right here. We come straight up. This is also this point on the plane z equals y. Since x and y are 1 here, we know that z has to be 1 as well because z equals y. So this point is 1, 1, 1, where all three of these planes intersect. So z is going to go from 0, the bottom, to z equals 1. So that's the biggest z can be in that picture. Now, what we really want to do to get the limits of integration for dy dz here is to look at what the shadow is of this solid in the yz plane. So we imagine having a sun way over here or a light source way over here on the positive x-axis and seeing what the shadow is on the zy plane. So this, for example, well, it's just going to be this triangle. The whole triangle is just going to go over here for the shadow, and this part will go to the y-axis back here. And this was y equals 1. We just said a little while ago where x and y are both 1. So that's just going to come up at y equals 1. And then this is z equals y. So this would just be z equals y in the zy plane. So we're going to have a triangle where we have the bottom here, the y-axis, and y equals 1, and then z equals y. So keeping that in mind, when I do this limits of integration, we already have the z going from 0 to 1. For each fixed z between 0 and 1, we go in the positive y direction. The first thing we're going to hit is y equals z, or the z equals y here. So y equals z to y equals 1. So it's going from y equals z to y equals 1. Or if you want to do it over here, it's going from y equals z to y equals 1. So that's what's going on with y and z. And the last thing to figure out, well, you take something in that shadow here in the yz plane, and you go in the positive x direction and see the first thing you hit and the last thing you hit. So in this solid. So the first thing we hit in this solid is this plane where x equals y, and then x equals 1. So x is going from x equals y to x equals 1, going in positive x direction. So x goes from x equals y to x equals 1. And so we have this triple integral set up then. We've interchanged the dz dx dy to dx dy dz, and those are the limits of integration finishing the problem. The last problem we want to do is, again, a problem involving interchanging the order of integration. This is what's given in the problem. And let's look at this a little closer here. We could figure out what's going on in the YZ plane by looking at these two limits of integration. In this picture, that's just going to give us this triangle in the back here. And I want to concentrate on this plane here. Where is that coming from? Well, if you look at what's happening to x, x is going from 0, 0 is the YZ plane in the back, to this plane. So this x equals this is this plane. So let me write that down. I'm going to write x equals this, except I'm going to simplify that. If this is equal to x, then 3x will be 6 minus 3y minus z. If I bring the 3y and z over, I'll have 6 equals 3x plus 3y plus z. So I'm going to write this as 3x plus 3y plus z equals 6. So that's this plane. Now, it's nice to concentrate on this because it tells us a lot of information when we have a plane like this. If I want to know where it hits the x-axis, what this point is, the biggest value for x, I can look at this plane and say, well, it's where the plane hits the x-axis. So on the x-axis, y and z are 0. So it's just going to be 3x equals 6, or x equals 2. So x equals 2 right there. For the y-axis, I'd want to take the intersection of the plane with the y-axis. And on the y-axis, x and z are 0. So we have 3y equals 6, or y equals 2. So that's where it hits the y-axis. And finally, for the z-axis, this point here, that's where x and y equal to 0, and you're just going to have z equals 6. So the intersection of this plane with the z-axis is at 6, and that's going to be the top point there. We also get other information like this line right here in the YZ plane. That's on the back here. If I want to know what's going on in the YZ plane, what the equation of this line is in the YZ plane, well, the YZ plane is where x equals 0. So I just take x equal to 0 to see where this plane intersects x equals 0, the YZ plane. And I get 3y plus z equals 6. That's this line. Now that's also the same thing as this line here. That's where this limit of integration is coming from in the end. So if I set this equal to y was what's going on in the middle here, y equal to this would be the same thing as saying 3y equals 6 minus z, or 3y plus z equals 6. So that's the same thing we just said. So this back line, this back line here we can understand just by setting x equal to 0 in this plane. So what we want to understand in this picture is what's going on the xy plane first, so this triangle down here, and to set up the limits of integration based on the picture in the xy plane. Well, we can see x is going from 0 to what we said was 2. We said this intersected the x-axis at 2, so this is 2 here. So x is going from 0 to 2. And then for each fixed x in the xy plane, we want to know what's going on with y. Y is going to start out at 0 here and go to this line here. Well, it starts out at 0. Let me put that in. So I put a 0 here. But what's this line? Well, again, if we want to know where this line is, it's the intersection of the plane we have, this plane that we were just talking about, with the xy plane. And on the xy plane, z equals 0. So I just set this equal to 0. And the intersection then is 3x plus 3y equals 6. I can divide by 3 there. I'll have x plus y equals 2. So that's this line. X plus y equals 2 is the intersection of the plane with z equals 0, the xy plane. So this is x plus y equals 2. When we simplified that before, so we have x plus y equals 2. So we're going from y equals 0 to y equals 2 minus x. So that's a 2 minus x. Y is going from 0 to 2 minus x. Finally, for z, we want to imagine going in the positive z direction. The first thing we hit on the solid is the bottom part here where z equals 0. Give me the 0 there. And the last thing we hit is this plane. So we're going from 0 to this plane, and then we keep going. At this plane, though, if we're going straight up, the last part of the solid, we're going to get then this plane, and we want to solve for z. Z is going to be 6 minus 3x minus 3y here. 6 minus 3x minus 3y. So again, the z equals this is just the equation of this point. And that's the last thing you hit if you're going in the positive z direction. So that's the setup for this triple integral. And we've interchanged in the order of integration here from dx dy dz to dz dy dx. And that finishes this problem and this lecture.